All right, thanks for coming. Just as a warning, I'm going to try and do some Wireshark demos, and I'm not sure how visible the screen is going to be, so if you think you might have trouble seeing, you can move up to the front. There's a few spaces closer up if you think you might have trouble. All right, so my name is Stephen Donnelly. I'm from Endace in New Zealand. We're one of the sponsors of Wireshark, of SharkFest rather. And this year we're sponsoring the Packet Challenge. So if you're doing the Packet Challenge, you can come visit us in the Packet Bay, and there's some Endace gear there. Have a talk to us about what it does. Apart from that, I'll try and keep any commercial content to a minimum, so I apologize for anything that does come through. All right, so this talk is about, there's a lot of talks here at SharkFest about use cases and case studies, looking at individual trace files and understanding how to dissect them and what the problems are. This talk is a little bit meta. So this talk is more about how do we go about doing packet capture? What are some of the important things about the process? How do we capture that information? And how do we do that in a kind of a structured way and not lose things? So why do we capture packets? There's this great t-shirt from the Net Reset guys. You can buy it on their website. PCAP or it didn't happen, right? So there's a lot of different reasons why people capture packets, but fundamentally the reason why we do it is it's ground truth, right? So if you have a network trace that demonstrates a problem, you can take that back to your ISP or your service provider or your application provider and say, look, I've got proof. I can see exactly what's going wrong. You know, here it is. You now have to go and solve that, right? If you're the network guy, you can use it to prove the application's wrong. If you're an applications guy, you can use it to prove that the network's wrong, right? It's great for finger pointing. But one question is a PCAP file really enough, right? So, you know, we tend to just do a quick packet capture and say, look, I've got the evidence. We're all done. That's it. It's as far as we need to go. But if you've been doing this for a while, like I think most of us have, you probably have on your laptop somewhere a folder, and it'll be called something useful like CAPs, or PCAPs, or MISC. And inside it, there'll be dozens of files with useful names like cap3.pcap, right? And the date on it is from 3 years ago. And you have no idea looking at it, looking at the file name at least, what it is, what's in there, why did you capture it, where did it come from. So looking at that directory kind of reminds me of a wall of cans with no labels on, right? You have no idea looking at those files. You've already forgotten. You did know back when you created those files. And you may have encoded into the file name like the name of the city or the name of the server or the application or something. But usually there isn't enough information there for you to really remember why did you take that trace file, what was important about it. So another way of thinking about that, you know, our packet traces is ground truth. I had a comment from one of our customers who said, packets don't lie unless you don't know where they came from. And so I was kind of thinking about that. I think there are a few cases where packet traces can be misleading, or at least where you can lose some of the context about them that tells you why they're important. And there's kind of two ways of reading that first one. You don't know where they came from. One of them is, in a lot of cases, you are not the person who does the packet capture. The packet capture is done by somebody else. It's a customer, or it's somebody in a different team, or whatever. Do you trust that person? Do you know that that file has not been tampered with? You know, so do you know where it came from? Secondly, if you're in a large organization running data centers around the world, and you're looking at that set of PCAP files, do you remember where you captured it from? Because a PCAP file doesn't tell you anything about where in your network you actually captured it. You also don't know if there was packet loss. So if you've ever run, you know, TCP dump or Wireshark, when you're doing a capture, it will tell you at the end of the capture whether or not during the capture process, the capturing system was not able to record all of the packets that were there, right? But when you save that to a PCAP file and then open it 3 months later, the PCAP file doesn't tell you whether there was packet loss at the time or not. So unless you remember to write that down, or just throw away the PCAP file and delete it, do another one, you're not going to know later on. You also don't know if files have been filtered, right? So when you did that packet capture, you may have filtered what you were capturing to reduce the bandwidth or whatever, but what the filter was is not recorded. So in a year's time, when you're looking at that trace file and there's no DNS in it, the question is, well, is there no DNS in there because there was no DNS on the link? Or is there no DNS in there because I filtered it out for some reason? Right? You have no way of telling. We also tend to assume that timestamps in trace files are correct, but we don't actually know that for sure. So if I'm trying to correlate a trace file against, say, an alert from an IDS or something like that, I ideally want to know that these two timestamps from these different systems are going to line up. And if I'm comparing trace files from different points in the network, if those clocks are synchronized, then I can understand how packets flowed through the network. So what you need is some metadata, right? So metadata provides that contextual information about the packet trace. So that's kind of a quick overview of the talk. Why do we need metadata? What would we use it for? What kinds of metadata are there anyway? How does that relate to packet traces? And then how can you actually do that today? So a couple of different ways of encoding metadata you can use with Wireshark. How do they differ? And what's the impact of that? Is there any reason why you would use one or the other? So again, why do we need metadata? And why do we do packet capture? Lots of different reasons. There's as many reasons as there are reasons why you do packet capture. One of them is scalability. So again, if you've got a large corporate network, you've got data centers all around the world, you can run a PCAP on lots of different devices within your network or in servers or client machines. And you really want to know where the data was captured from. Likewise, timing accuracy. Some people, particularly in financial institutions, are actually legally mandated to have their timestamps be accurate to within a certain standard. So in Europe, for example, there's the MiFID II regulations that say that you must record all the traffic in or out of your organization, your trades, if you like, and their market feed information, and you have to be within 100 nanoseconds of UTC. 100 nanoseconds? Microsecond. I think it's a microsecond, sorry. And the reason for that is the regulators realize that with financial trading automation, they need to be able to go back and reconstruct the timeline. You need to be able to prove that you didn't short a trade. So they need to know what information had you received from the market at the point that you made a trade going out. And they want to do that across the whole industry. So everybody has to be on the same time base. Packet capture quality is another good one. So no matter what you're using a packet trace for, the quality of that trace is important. If you don't know whether you've got packet loss, for example, or you don't know if a trace is filtered, then that changes how you interpret it. If you have a trace file where there was packet loss by the capturing system, you put it into Wireshark and turn on TCP analysis, Wireshark's are going to get confused because it's going to see things which it interprets as problems on the network, packets that are lost on the network, when in fact they were actually lost during the capturing process. So it does make a difference. Okay, so on to the what. So what's metadata? I think most of us have a fundamental idea of what we mean by metadata. The common example is EXIF tags in JPEGs, right? Take a picture with your phone, you get the picture. This is a picture that I took at SharkFest 16 in the sunny Netherlands. And the image viewer is putting some metadata on the side for us, right? So it's recording things like the actual time and date that the picture was taken as opposed to the file timestamp. Some data about the size of the image, the type of device that captured it. Okay, it was an iPhone 6, and the f-stop, and the speed, and sensitivity, and so on. It's running at 160 ISO, so that's why it's all grainy, right? It actually looks much darker than that in person. And it doesn't record the location, the name of the location, but it records the GPS coordinates. So from that, the image viewer can then draw you a nice map, and it can name that we're in Arnhem. Curiously, if you do open a JPEG file in Wireshark, it will dissect it and it will show you the EXIF tags. But it's not very user-friendly. It's kind of a little bit hard to interpret them. So I haven't done an example of that. I'm sure you should try it sometime. But when you think about a photo, the thing about a photo is it's a single point in time, whereas a packet capture is more like a video, right? It covers, has a start and an end, but it covers a certain period of time. So we can think about metadata in a couple of different categories. There's the things that are static, they don't change. So the camera that you're using for shooting the video doesn't change. The capture system, usually during a capture, will be constant. So there's a whole lot of information you really only need one copy of. Things like what was the machine, which capture interfaces were you using, and so on. Then there's dynamic capture information. So what is information that potentially changes while you're doing a packet capture? Clock synchronization is one. So you might check that your clock synchronization is good and then start a packet capture, but while it's running, you lose your connection to the timing server, and so the clock can start drifting off. Same for link states, particularly if you're capturing on more than one interface. Some of those links might go up or down while you're doing a capture. If it's a 5-minute one, it's unlikely. But if you're capturing for days at a time or weeks at a time, then it's inevitable it will happen. Similar for optical power. You might not think optical power would change much during a link, during a packet capture, but if somebody is plugging and unplugging cables, doing patches, or running a ditch digger through something, then it can change as well. And then finally, there's sort of post-capture annotations. And the killer app for this in Wireshark has been user comments. So this is one of the most requested features up until the point that they put it in. Now people don't ask for it so much. But there's all kinds of things that you could add to a trace file after you've captured it. So events and alerts from your IDS system, you could annotate those back into a trace file after you've done the capture. Flow records, so you could do sort of NetFlow style or IPFix style flow information. DPI, so if you have something that runs across a trace file, analyzes the application and gives you more information than just the source and destination ports. It tries to tell you what that application is. There's all kinds of artificial intelligence stuff, IP reputation scores, anything like that you might want to keep, you could write into the trace file afterwards. So if we kind of try and break down some categories of kinds of things we might want to store into who, what, when, where, how, and why, the same way the reporter might report on a story, if they're any good. And I've sort of tried to think of a broad range of different types of information you might need. So information about how something was captured, what the equipment was, who actually did the capture, what was their user ID, was there a warrant associated with that or something? Why? Was this triggered by a IDS alert, or was there some user reporting a trouble ticket, or something like that? Where within your network was it actually recorded? What was the clock synchronization doing? And of course the actual trace itself, if you like, the packet contents, capture filters and search terms and things like that. Okay, so how do we go about doing all of that? First of all, let's go back in time a little bit. How many people are capturing using libpcap? Sorry, start again. How many people are capturing into the PCAP file format today? Anybody? Just a few? 1, 2, 3, 4, 5 out of 30 or 40? Something like that? Okay, so not too many. How many people are using PCAP-NG? You're capturing PCAP-NG? 1, 2, 3, 4, 5, 6, a few more. Okay. And then there's ERF, which is the end-days format. So obviously I capture in that. Probably nobody else, but there we go. So if we think back to libpcap, I mentioned earlier that libpcap doesn't tell you things like whether you dropped any packets while you were capturing. TCP dump does, and when you finish capturing, it'll say, oh yeah, you dropped all these packets. But it doesn't write that into the file anywhere. So when you think about the PCAP file format, it's pretty simple. There's a file header, which has got a few fields in it. It tells you what the timestamp resolution is. You get the version of the PCAP format itself, whatever the local time zone was, if you weren't capturing in UTC for some reason. There's a timestamp accuracy field in there, but it's unused. So libpcap actually doesn't read or write that field. It's just 0. So nobody actually knows how to interpret that. There is a capture length. So remember, when you're capturing packets, you may not be capturing the full packet. You might be truncating them short. So you can record that information. And then finally, the link type. So Wireshark doesn't know how to interpret a PCAP file if it doesn't know what sort of link it was on. And libpcap, or the PCAP file format, only supports one link. So you can't have both Wi-Fi and wired Ethernet within a single trace file. Or if you do, you can only do it at the lowest common denominator. And then finally, you get a series of packets, right? So every packet has got a timestamp on it. It's got the length of that packet that you captured and how long it was originally. So if you're not truncating, those numbers are pretty much the same. And then finally, the packet contents. Let's see. So I'm going to try to do this. Do a demo. See if I can blow that up a little bit. So, okay, so here's a PCAP file in Wireshark. It's a fairly modern version of Wireshark. It's not a very interesting trace file. It's just something I happen to have lying around. But I kind of want to point out what's not there. So what do you not see? First of all, you don't see the PCAP file header, right? It's not there in the packet list. Wireshark doesn't display that directly. But you can get some of that information. And a couple of things you can notice. First of all, when we look at the frame information, you notice that it says what the capture length was, but there's no interface information here. Because as far as PCAP is concerned, there is only one capture interface. And if you capture on the any interface in Linux, for example, you will get packets from more than one interface, but you won't know which packets came from which interface. So it's not a good use. It's not a good format to use for that. And then if we look at the statistics menu, capture file properties, unfortunately that dialog doesn't scale when you scale the background. So it's a little bit hard to see. But what you can hopefully see here is there's a few of these unknowns. There's a whole bunch of fields here: hardware, OS, application unknown, packet drops unknown, capture filter unknown. So this is just reminding you, if you like, that PCAP doesn't tell you any of that stuff. It might be that there were no packet drops, but you can't tell. Okay. That's not good. Sorry about that. Okay, so, and if we think about our coverage map, what does libpcap cover out of all that information that we wanted? Well, it gives us a timestamp for every packet and the contents of the packet. And in theory, it gives us a timestamp resolution. It's either microseconds or nanoseconds. It doesn't mean that's the accuracy. It just means that's the format that the timestamp's encoded in. It doesn't really tell us whether it's synchronized to anything or not. So, not very good coverage, really. Fortunately, there is good news. The good news is people thought about this problem quite a while back and came up with the next generation of PCAP, PCAP-NG. It's a little bit different to PCAP, which is a very simple format. It's block-based and has what we call TLV, so type length value options. So there's a lot of different options defined. There's over 30 different tags, and there's a number of different block types. It does support multiple capture interfaces. So if you're doing a capture, say, on your laptop, and you're capturing from the loopback interface and the wireless interface and the wired interface, you store it in PCAP-NG, you'll be able to tell which packets are on which interface. And it's extendable. So there are vendor extensions, and there's a working group who actually add stuff to it all the time. There's been a couple of IETF drafts going back to 2004, and another one in 2014. As far as I know, it wasn't accepted as an RFC, but there were published documents about this stuff. It's been supported in Wireshark since 2009, version 1.2. It's been readable by libpcap since 1.1, which was in 2010. And what that means is any application that reads files using libpcap can automatically read PCAP-NG files. You don't get all the benefits of PCAP-NG, but it can at least read the files. So there's no really good reasons not to use PCAP-NG as far as I can see. You can always convert PCAP-NG to PCAP. You can down convert it. Converting up you can't do because you don't have that information. And then finally, the nail in the coffin, if you like, it's the default format in Wireshark since 1.8 back in 2012 for saving. So if you're doing your captures using dumpcap or tshark or Wireshark, it will be recorded in PCAP-NG by default. So you may already be using it without having noticed. And then the standards group itself, you can find it on GitHub. That's the documentation for the format. So if you have a quick look at it, how the blocks work, the things that are in italics are the optional parts. So again, like PCAP, you have a section header block. It's kind of like a file header with a version in it. You can store all that information about the hardware and the OS. There's an interface description block. So each interface that you're capturing from, you store a bunch of information about that. Some of it's, a lot of it is optional, but you can store things like a capture filter on a per interface basis. Also the timestamp resolution, the speed of each link, and so on. You can give it a name. The packets themselves are in what are called enhanced packet blocks, where you get the interface ID, the timestamp, the lengths are all mandatory, and you can optionally have information like packet drops. Then there's a few other ones. There's a name resolution block, which can store IPv4 or IPv6 name resolutions. And you might say, well, you know, why do I need to do that? If you captured a packet trace on the network here, you could use DNS to look up the IP addresses of all the machines, but it's probably an RFC 1918 address space, right? So if I then close Wireshark and go home and open that PCAP file, all of a sudden I can't resolve those names anymore because those names are not global on the internet, they're local to that local network. And sometimes the names are really useful because they give you a good hint what a machine is supposed to be doing. So what happens with PCAP-NG, if you turn name resolution on in Wireshark, when you save the file, at the end of the file, it stores all those resolved names from the network you captured on.
So it takes the snapshot of the moment of the capture so you have reference point.
That's right. So it actually, Wireshark itself will resolve the names if you enable that in the settings, and it will then record into the trace file what all those mappings are. So when I open the file, I don't have to kick off a resolver to go and look up the names. It just uses the ones that are already stored. Pretty handy. Then there's an interface statistics block, which you can drop in periodically or at the end of the file. One per interface, per capture interface, with information about received and dropped and filtered packets. So there finally we have something that will tell us whether or not we actually dropped any packets. There are a bunch of other blocks as well, which have been proposed in the standard but not implemented. Compression, encryption, different types of indexes, monitoring, vendor extensions. There are some vendor extensions which are supported in Wireshark that people have proposed, but there's not a huge amount so far. And we see what this would look like in terms of the structure. So a file that's saved by Wireshark will look like this. There will be a single section header block at the beginning. You get one interface description block per interface, so 3 in this example. A whole bunch of packets for the packet blocks, and then at the end of the file you get those name resolution blocks, which are still just blocks within the packet, and you get as many of those as you need in order to resolve all of the names in the file, all the ones that could be resolved. I think they're about 2 megabytes each, the maximum size, and it'll just create as many as it needs. And then right at the end, Wireshark will write out a statistics block for each interface that it captured on. So that's how it can tell you what the packet drops were. Okay, so let's try this again. Have a look at the PCAP-NG file. Blow this up a little bit. Hopefully that's somewhat visible. Okay, so again, here's a bunch of files. Now you notice one thing here is that a lot of the IPs are now resolved. Okay, so those are all things from my local network back at home. They're all RSC 1918 addresses, but the name resolution is stored, so you can actually see what the names were when I did the capture. If we look at a frame, one of the things we notice just here is it tells us an interface number, interface 0. And I think if we look through the files a little bit, where are we? Through the files a little bit, we should see some packets that are captured on interface. There's one. So there's interface 0. Okay, now what does 0 versus 1 mean? It's a good question. So if we have a look, if we open one of these frames, then it tells us here, this particular frame is captured on interface 1, and the device name was device NBPF, some horrible hex thing. Right? So immediately that tells me this was captured in Windows, because that naming scheme is how Windows names its capture interfaces. Now that hex number is a GUID, so it's a globally unique identifier, and you could use that to recognize the machine that you did that capture on, right? So you could look at different trace files and go, oh, these two trace files are actually captured on the same machine because they have the same GUIDs. It's not very human friendly though, so I wouldn't know looking at that whether it was a Wi-Fi interface or the wired interface or whatever. If you're in Linux, it's the other way around. So if you're in Linux, that will be recorded as ETH0, right, or WLAN 0 or something like that, which is very descriptive, but it's not globally unique. So you kind of tend to get one or the other. The two platforms are not quite the same. What are some other cool stuff we can do? So if we have a look in the capture file properties, I apologize for this being small. What we can see now is this time some of these fields are filled in. So the hardware is unknown. The OS is 64-bit Windows. The application is dumpcat 227. Interestingly, in Linux, the hardware is filled in. So in Linux, it will say, Intel Xeon something or other, 2 gigahertz, whatever. And I think it might give you the kernel version. And it'll give you the Linux distribution name and stuff as well. Then we've got the capture interface section. So now we've actually got some named interfaces. We've got these horrible names. You've got the drop count. So there's one packet was dropped on that interface and none on that interface. You've got a capture filter that was used on each interface. So I've got not TCP port 81 and not TCP port 82 on here. And the packet capture size limit, 262,000 bytes on each frame. Okay, and then finally we've also got capture file comments. So this box down the bottom will record any capture file comments that you make, and I've got one here which says add name resolution. So for that particular trace file in Wireshark, I enabled name resolution and saved it so that you got all of those resolved names. And you can see those if you look in resolved addresses, statistics resolved addresses. And it will list the sets of things that it's resolved, all the ports, MAC addresses and stuff, prefixes. Now one thing you may have noticed looking at this trace file, we didn't see the section header block, right? We didn't see the interface description blocks. You can see some of that information by looking in the capture summary, but you can't see the actual contents of those things themselves. So if there are fields in there that Wireshark doesn't understand, then they don't show up in the UI. But there is a trick. You can go to View, and if you go down to Reload as File Format / Capture, which of course is Control-Shift-F, as we all know, then it changes the view of the file completely. And what we get is a single entry. So open this up a little bit. Which has the PCAP-NG file format in it. So all of a sudden we can now see the section header block, the two interface description blocks, and each of the enhanced packet blocks. And if you open these things up, you can see the various bits of information that are stored within each one. So there's the block type, there's the block data, the magic numbers, the options. There's strings that we were looking at earlier. So there's the 64-bit Windows, the file trace comment, and so on. So if you're interested in seeing what is the contents of the PCAP-NG format, you can do it by opening it as a file instead of as a packet trace. That's kind of interesting. And the information about the interfaces is there. If we scroll down to the end, we can see the name resolution block, which is where all those resolved names are, and then the interface statistics blocks. And there is a little comment on the interface statistics blocks. Open it up. Options. Counters provided by dumpcap. So that's a comment that Wireshark adds automatically to let you know that it was the dumpcap tool which calculated those statistics and put them in the file. Okay. Scroll through again. So, coverage map again, looking a lot better. So PCAP-NG stores far more information about the trace file, which is going to be useful to you later on when you're trying to figure out in 3 years' time, why did I do this trace in the first place? You've got information about multiple interfaces, your link names, you've got the comments, you've got the capture system, the link speeds. Link speed is kind of important. If I see a 900 megabit spike, was that 90% of the link rate, or was it 9% of the link rate? You need to know what the link speed is in order to interpret those bursts. A few things that it doesn't get yet, so information about the clock synchronization, some of the information about the system is a little bit sparse, but you have a get out of jail free card, which is this one, the comments. So anything that's not covered automatically by Wireshark, you can go and manually add as a comment. So something to think about when you're doing a capture in Wireshark. Think, next year, what is the information I need to know about this file? Just add it as a trace comment and save it. And if you look at the USB stick that they hand out for the packet challenge or Laura's labs, the files that are on those sticks are PCAP-NG format, and they have comments in them, which tell you about what's interesting about that file. So it's very useful. Okay. There's only one other format that I know of which does a significant amount of metadata inside inside Wireshark, understood by Wireshark, which is the ERF, Extensible Record Format, which is the one that is generated by our cards and equipment. It's a little bit different in approach. So rather than a file type, it's more like just a continuous stream of records. There's different record types, fixed headers, and so on. The ERF format that we produce has been supported since 2003, Ethereal 0915, so it was a little bit before it became Wireshark. There is full support in modern Wireshark, so if you are using DAG cards or systems, we're actively working on support in Wireshark. Please give us feedback. There is a complete dissector, so all of the metadata that we do is available in there as display fields, so you can use display filters to look at them, and expert info and so on. And we have support for metadata in Wireshark since 2016, Wireshark 2.2, and then we added support for comments in 2017 in Wireshark 2.4. So it's relatively new, but seems to be working well. The basic scheme is that we insert metadata on a periodic basis rather than just once at the beginning of the file. That kind of helps us deal with the dynamic metadata that changes over time. A few things about it. It has a hierarchical addressing scheme. So if you remember with PCAP-NG, you had an interface name which was dev some GUID. In the ERF format, we record information separately about the host, which capture card it was, and which interface it was you're capturing on. There's also the time the metadata was generated. There are multiple sections. There's 160 different tags defined so far. I think there's actually a few more since I wrote that slide. TLV again, so similar kind of approach to PCAP-NG. Up to 64 kilobytes of metadata per record. And we have an append on update policy. So what I mean by that is, if you want to change a comment in Wireshark, what it will do is it will just overwrite the comment with your new comment. In ERF format, if you want to change a comment, it leaves the existing comment there and just adds a new one after it. So you always have this history of what was previously there rather than overwriting stuff. So what it looks like in a trace file, as I said, it's just kind of this periodic thing. The blue ones are packets, and then the yellow ones are provenance records that get dropped in. Typically it's once a second, but you could make it more rapid or slower depending on what you want. The provenance records are broken up into a few different sections. So we've got, which is kind of similar in a way to the PCAP-NG blocks, but not exactly the same. There's information about a particular capture. So that would be, why am I doing this particular capture now? You can give it a name, which would be similar to a file name, but you know that if you email it to somebody, they're not going to lose that if they rename the file, because it's actually inside the file. Application version ID, the user ID, the time zone. If you're capturing in Wireshark, it will get the user ID from the operating system. So it'll actually get your login name for who it was who actually did the capture on that particular machine. You get a bunch of information about the host, so the host name, OS version, CPU, RAM, all that kind of stuff. Some of the fields like the organization and the location you'd have to fill in yourself as a template. There's information about what we call a module, that's kind of device, that's your capture card. You know, what model was it, what was the firmware version, all those sorts of things. What was the clock synchronization state. Information about each of the interfaces, what were the SFP vendors and models, the link speed that was negotiated, all those kinds of things. And then information about each capture queue or stream, if you like. Okay, see if we can do a demo of that. Yep. So here is a trace file in ERF opened in Wireshark. One thing that you notice straight away, just here, is at exactly on the edge of the second at 1948-44, there's an ERF provenance metadata record. So this is one of these periodic records that gets dropped into the trace file. So with PCAP-NG, if you want to see that metadata, you have to switch to file mode. In ERF, because we just treat it as if it was a packet record, you can see it directly in the packet trace. If you don't want to see it in the packet trace because it annoys you, you can just filter that out. It's using a display filter. And you'll see, as we scroll through the file, that these things turn up periodically at the end of each second, or the beginning of each second. So if we pick one of these, we can open up the format, have a quick look. There's the capture section, so information about this particular packet capture. So I can put in a name for the packet capture and descriptions and so on. The user who was logged in, the application that was used to record it, what my time zone was, all those things. I can put in information about the host, so the host name. Some of these are filled in automatically, so it's things like the host name, the serial number, the model, the amount of memory, that's all collected automatically, whereas things like the organization name and the description are entered manually through config files. And we also get the operating system and all that kind of stuff. And we get information about the packet capture device. So in this case, it's a DAG10X4P model. And there's quite a lot of information in here about clock synchronization. So if it's PDP, it'll tell you which grandmaster is it listening to, what is that grandmaster using for its clock reference, how accurate is it to UTC, is it an auditable time to UTC, which a grandmaster will tell you. And then we get information about each interface. So in this particular case, the capture interface called port A is a 40 gigabit per second Ethernet, and it's made up of 4 10 gigabit interface modules, so you get information about all 4 SFP devices there, including so you got your speed there, 40 gigabits, and you've got your receive optical power on each lane, and the transmit optical power on each lane. There's information there about the timing port, which is used for PDP protocol, so that has the address of that interface, the fact that it's up at a gigabit, and so on. And then we get information about capture streams, including the drop counts. So there's a couple of counts there for whether any packets have been dropped during the capture session. And then if we go into our capture file properties, again, apologize for the size, you can see we've got this kind of more Unix style hardware description where we've got the system name, the make and model, the CPU type, and so on. This was CentOS 7.2 capture application. You get the host name. It's a little bit hard to see from where you are, but the host name automatically has a host ID, a card ID, and an interface ID as separate fields. So that lets you address within your organization exactly where that particular interface is. We record you've got the capture filter, you've got your packet drops, and so on. And if we had file comments, they would show up down here. So the screenshots are in the slides in case you want to look at it later. It'll be up on the SharkFest site, and you can have a look at some of those things. They're a bit hard to see. So coverage-wise, pretty good, I think. We've got a lot more tags than are in the PCAP-NG format. There's still a few things missing. So one example is display filters. So you notice we talked a lot about capture filters and Wireshark. So Wireshark's got two different concepts. The capture filter is the one that's applied before Wireshark sees the packets. And Wireshark will record that when you save a file. But you can also apply a display filter and then export the packets under a display filter. When you do that, Wireshark doesn't record what the display filter is. It'll still tell you what the capture filter was, but it won't tell you what the display filter was. So if you're going to do that, you may want to cut and paste the the display filter, and stick it in as a file comment before you save it. Otherwise, you're not going to know what it was. Another one that's kind of interesting is packet brokers. So a lot of people are using an external device for doing packet aggregation. It might be a Gigamon, or there's a bunch of different vendors who are here today who do that. It would be nice to be able to collect some of that information and store that in the trace file as well. So quick note about comments, because comments, as I said, are kind of the killer app for metadata in Wireshark. PCAP-NG has got a comment string option that you can put anywhere. You can just kind of shotgun it in there. Wireshark implements comments in the section header block as a capture file comment, and any comment in a packet block shows up as a packet comment, which works very well. ERF also supports comments, but it does it by inserting a complete provenance record. So general comments records that we put in will show up in the top level in the capture summary, and then if you want to add a comment to a particular packet, you insert a provenance record before it. The provenance record has got the generation time, it's got the user ID of the person who added it, the host ID of the system that you added the comment on, which might not be the same machine that you captured the file on, and the username of the person on the machine that added the comment. So all of that stuff is recorded as a kind of an audit trail, if you like. So comparison, I guess, PCAP-NG is a file format specifically. It only stores one set of metadata no matter how long the file is. If you're doing it over a long time, you can break it up and have multiple files. There's another way of doing it. So it works pretty well if the capture situation is static. So if you're doing a short capture on your laptop, it's going to be fine. If you're in a complex environment or you're doing long-running captures, you might want to consider something else. With ERF, we record all of the metadata every second, which seems like overkill. Why do I need to record the host name of the system every second? It's not going to change, right? well, probably not going to change. One of the reasons is if you've got a trace that's hours long, I can go into the middle of it and cut out a 1 minute section, and I know that the metadata is within that subset. I don't have to go back to the beginning of the file to try and capture the section header. It's pretty lightweight. You're adding 1 record per second for each capture card. It supports multiple hosts and so on. And so I think it's better for long-term or continuous capture where the environment's going to be changing. So in conclusion, trace metadata provides critical context for interpreting your trace files when you come back to look at them later. The interpretation really does depend on the context. If I'm doing a capture near a client versus near a server, I'm going to see different effects. I'm going to interpret that in different ways. There's different types of metadata. There's static, dynamic, and post-capture. And having a way of dealing with all of those is really good. Having used this for a little while, automatic metadata is the best metadata. So if I run Wireshark, it saves a whole bunch of information. I don't have to do anything. Then I know it's going to be in there. If it's manual metadata where I have to type comments in and I have to do a whole bunch of bookkeeping, people are lazy and they tend to forget. And so when you open that file in 3 months' time, there's a good chance it's not going to be there. And the good news is it's available in Wireshark today. Right? So thanks to these developers, we've got formats supported in Wireshark where you can record rich metadata and view it. So please use it. You know, everyone, if you're capturing in PCAP-NG, consider using PCAP-NG. Encourage other people to use file formats that have richer metadata. If you're going to send a file to a colleague, see if they all take it in PCAP-NG rather than PCAP, and they get more information about it. Share rich formats with metadata, but keep in mind anonymization. Right? So if I capture a file with PCAP-NG and I want to upload it to ask.wireshark.org or something, I probably have more anonymization to do on that than I would if it was a PCAP file. So you do need to be aware of that. You can always down convert, so you can convert from these formats back to PCAP and strip everything out, but of course you lose all that context. So it's a balancing act. Okay, thanks. Any questions?
So on your network, your name resolution blocks,
Mm-hmm.
you're doing like a rolling ring buffer style capture with T-Shark command. How are those handled? Are they every time the file closes, does it append those at the end, or does it wait until the end of the whole thing? Then does every individual file have all the same name blocks?
Good question. So the question was, if you're doing a rotating, like a long-term capture with T-Shark, and you're outputting to multiple files, does it store name resolution blocks at the end of each file? I believe it does. So each time it closes the file, Wireshark flushes out the name resolution blocks that it's got. I don't know for sure whether it then empties the tables and then starts again from the next file. I'm not 100% sure on that. So I would assume that it does, but not 100% sure. To check that.
You're looking at the packet comments in Wireshark.
Mm-hmm.
Do you know if there's a way to have it? Can you do like bulk operations, like, or if you want to put the same comment on 5 packets, you just select packet 1, add the comment, packet 2, add the comment, do things in.
Good question. So the question there was, can you do bulk operations on packets in order to add comments? So can I just automatically add a comment to a whole bunch of packets, for example? I don't think the Wireshark UI lets you do that. So in the Wireshark UI, you can right-click on a packet and you can say add a comment. If you're using T-Shark, there are command line options you can use to say, you know, to packet number 973, add this comment. And it'll then resave the file. So I think you could probably write a script and you could stack a bunch of options on T-Shark or EditCat maybe and have it add comments to multiple records. And that's a way to go back and annotate things like IDS alerts and stuff too, as comments. Yep.
You mentioned, you know, in your matrix, the geospatial information.
Mm-hmm.
Talk at all about the strategies for like incorporating information from
Right. So the question there was geospatial information in trace files as metadata. So are there tools available, I guess you're asking, for...
Yeah, everybody always talks about Kismet.
Right.
Sometimes we receive data with geospatial information already in places like PPI headers, but don't seem to be standard ways of, say, integrating it with something like a GPS feed in tools like Wireshark or network capture.
Yeah, that's a really good question. So Kismet, as you noticed, is a war driving app, if you like. So it's a Wi-Fi capture system where you can drive around. You can put a GPS feed into it, and it will record the location as it's moving, so you can map locations of sources and stuff. I'm not aware of other specific tools that do that today. We've defined fields for lat long and so on in our format, but we don't specifically do that. Most of our capture systems are static. I believe that there was a proposal for PCAP-NG to record some mill standard location formats, including pointing directions. So if you've got a directional antenna and you're pointing, northwest and so much elevation, you can record all of that stuff in the stream, which is pretty cool. I haven't actually seen anyone do it, but the proposal is there. Anyone else? Okay, so if you've got any other questions, I'll be around for the rest of the conference. I'll be hanging around probably the packet bay most of the time. We do have some equipment there if you want to have a look at it, or if you have any other questions. Otherwise, we'll let you go a little bit early, and we can all have some more coffee or tea. Thank you.